Hello, everyone. Nice to meet you all, and we are pleased to welcome you today to our webinar, and especially to focus on how to properly use wind data in wind comfort analysis. And today I will be joined with Guillaume Cagnot,
Hi everyone.
who is the expert at Methodyne, and I'll let him to introduce himself.
Yes, thanks Guillaume. I'm a technical product leader for Urban, working since almost 15 years next year. And I'm very happy to be here today.
And I'm Guillaume Vervou. I'm the business manager of the offshore product line. So we're managing together all the aspects for the urban product line at Methodyne. And today, for the content of this webinar, we will focus on many topics. And the first one will be on the methodology to assess the wind comfort. After, we will briefly review what will be the technology of anemometers at the weather station, and especially after this, the topography effect, and especially the orography and roughness effect on the measurement. After, Guillaume will provide you a first aid kit around the wind data, and especially with examples of differences between weathers and weather data from the mast compared to a project. On the two final step, we will focus on where to collect data. And at the end of this webinar, we will have a Q&A session. So feel free to use the panel chat to ask some questions, and we'll happy to answer it at the end of this webinar. First of all, I will present you quickly Methodyne for the non-beginners of Methodyne software and expertise. Methodyne is a well-known company for the forefront of technology and innovation around the wind engineering, climatology, and meteorology. And we are based here in France, but we have offices also in Northern America, in India, or also in China. And today, our aim is to develop software around CFD, especially for the wind flow and solar radiation. And we are here to provide wind engineering expertise to our different clients and their project, especially if you are on the urban side as an architecture office, urban study plan, or other comfort analysis or wind analysis around a project. And we deliver today tailor-made studies and climate services around all over the world. And now we will focus on the first part of this webinar, and I'll let the floor to Guillaume.
Thanks Guillaume for this introduction. So I'm very happy to be here today. This webinar was a request by many of you. So on the next slide, I would like to have a recap of why do we need to get good wind data. So first, a recap, and also, by the way, you have a webinar about the wind comfort thematic. So this is available on our website. So a quick overview. So how do we do this kind of study? You need data, inputs, so climatology data. This could be a frequency table or can be time series. And then you compute several wind direction every 20, 30 degrees, and you assess the effect of wind with respect to obstacles. You post-process in the last part using your pedestrian wind comfort rule to get a pedestrian comfort map. So this is where we get, and now the question: how can I be sure I'm relevant, I'm good? So there are many bias. If you come back on the previous slide, there are different bias. First bias is input data. So obviously, if your obstacles, your buildings, your trees, your topography is not well designed, it will affect the pattern of your wind. Second is the wind data, and this is where I'm getting to. And the second bias is, or third bias, sorry, is the CFD, so input and CFD. The CFD, we have wrote many papers about that subject. So you can have a look in our webpage, and roughly we get, to give you another of ideas, 5% error with comparison with wind tunnel over the mean speed. So we know about, we have an idea about error under that subject, but what about the inputs? So today we're going to talk about the wind data inputs. So let's focus on where do we get data from? This is the first question. Let's have a look on anemometer technology at the weather station. This is the first thing. So there are different of them. You probably know the first one, which is the windsock. The windsock is the most famous and the most spread around the world. It is mainly set up in a small aerodrome. It is not only a weather vane, it can also estimate wind speed. If you have a look, you have stripes, red and white, and each stripe that's going to inflate it, you have an increase of wind speed between 3 knots to 5 knots depending of the country. 3 knots in US, 5 in France. So 3 knots, this is 5 kilometers, a bit more than 5 kilometers per hour, and 5 knots is 9 kilometers per hour in France. So in total for France, 5 stripes multiplied by 9 kilometers per hour, this is a maximum of 45 kilometers per hour. So this is basic, but it is only visual data. It's not this one I'm going to use. Next one is cup anemometer. It is called also Robinson from the inventor from the 19th centuries, and it can measure the wind speed and wind direction. It is made of 3 to 4 cup or half cup, about the size of a tennis ball. And when the air flow around this cup is going to rotate, and it will turn the shaft and proportionally to the wind speed, to the mean velocity of the wind. To give you an idea, the 1 revolution per second of this half cup is equivalent to 1 meter per second for a standard anemometer. So this is very easy and to set up this kind of installation, and it can range to 200 km per hour. So it's very nice for events like extreme event like storm. The bad thing, but it's not really useful for our case, it's to catch very fast events such as gust events smaller than a few seconds event. So it's not our purpose today. It's not for safety. So usually with this kind of cup, you have a weather van to catch the wind direction. This technology is the standard for wind assessment for wind energy. When we conduct wind resource assessments, we use this kind of cap anemometer. No, not last one. The third one is a vane anemometer. It looks like a small airplane. Like the cup anemometer of Robinson, the axis is horizontal. And the last one, this is from the 19th century, it's called ultrasonic anemometers, because, well, there is a sound wave to measure the wind speed and the wind direction. The big advantage of this technology is that you can easily set up in extreme condition in remote sites, such as an island or a platform on the sea. So there is no mechanical maintenance contrary to cup anemometers. And the second advantage is that it can catch the turbulence very very accurately. So what you will get usually is cup animators. This is the standard word. Sometimes you could find ultrasonic, but it's not that often. Okay, so now we have a look. Let's move to the next subject, which is the topographic effect. So when we are talking about topography effects, it is not in the common sense, it is in the meteorological sense. Common sense means the orography, so the hill, mountains, and here topography actually represents more than that. It's orographic effect and land occupation effect, or also called roughness effect. So this is both combination. So both will affect the wind. So globally, the mean velocity is a function of the topography, of the orography of the site. If you are here on this example on the top or the bottom of the hill, of the land occupation or roughness around the seats. If you are in the countryside or if you are in the city, it will affect the wind by the shear layer on the surface. The mean speed will be function of the height above the ground. You will see later a profile, a wind profile that's going to increase with respect to height. And it will be function of the obstacles nearby, buildings, trees. I will talk briefly about that later, but it's not the subject today. Okay, so now let's move to the topographic effect. I would like to give you some order of magnitude. So remember we can derive two effects, orography and roughness. If I focus on orography, if my reference is flat ground, and I will compare with the same land occupation, of course. So you will get 50% less wind speed at the bottom of the hill and 50% more wind speed at the top of the hill. Here we are talking about the mean speed, but you have to consider also the wind direction that's going to be affected by the orography. So this is for orography. For the roughness on the flat ground, if your reference is open country, if you compare to what you have on the shore, you get 40% more wind speed. On the opposite side, if you're looking at what you have on the downtown at same height, so here it's always 10 meter high, you get 50% less. So you see how orography or topography will affect a lot your mean speed. So how we can solve this issue? I would like to introduce to you some regulation we have in Europe. On the next slide. It's so we have Eurocode. This is a standard to compute the wind load over structure. It's a share regulation for a country in Europe. There are some annex for each countries. But here we talk about only about safety issue, not wind comfort, but it can give you some rules. It's quite interesting. So they talk in this paper when do we need to take into account orography effects. So there are two rules. The first rule is whenever your orography will increase, your local orography will increase your local wind speed more than by 5%. So it's when you need to take into consideration orography. And the opposite way, when you have an orography which is more than 3 degrees, 3 degrees is roughly 5% slope, you need to take into account orography in your computation because it will affect your wind speed. And you have to consider around your buildings a distance of 10 times your local isolated orography effect. So if you have a cliff, let's say, for example, of 50-meter high, it will affect around a radius of 500 meters around your project. So will it affect my project or not? This is the rule. So 5% of slope, local slope, and you have to look around the local topography by an order of 10 times the height of this accident. Okay, so let's move to the next slide. Now, I would like to talk to you to the roughness effect. So I've plot here the wind speed with respect to the height above the ground for several land occupation. On the left one, you have the city. So when the roughness is very high, 1 meter. And on the other side, you have land occupation, very flat. It is the sea, the ocean, with roughness lines very small, about millimeters. So what you can, there are two information here. The first one is that if you have a look on the wind profile, all of them increase with the height, with respect to the height, with a special shape. And there are some mathematical rules to interpolate that. And the second information is that if you have a look at 10 meter high above the ground, if you compare the wind speeds in the city at 10 meter and the wind speed above the sea, it is you have 3 more wind speed above the sea than above the city. Makes sense. When you are, if you're going to nearby the seashore, you experience more wind speed. On the right card, you have same approach, except that it's not coefficient, it is the real mean speed expressed in kilometer per hour for different wind profile according to different land occupation. What you could see is that the increase is not as fast for each land occupation. For open country with smaller roughness lands, it will increase fastly than downtown. Makes sense? We already explained that on the left card. Okay, so let's move to the next slide. Now I introduce the shape of the wind speed. So as I said, there are some mathematical interpolation of this wind profile. It could be exponential, it could be power law, it could be logarithm. It's whatever you want to define it. In Europe, we express it as logarithm. I know in other countries it's different rule, but at the end it is always it's almost the same. It depends of the coefficient behind. The idea that the wind speed is expressed by a coefficient lambda depending of the roughness of your site or your land occupation, depend of the Z0, which is the roughness length. It depends also of your reference wind speed. This reference wind speed in this formula is expressed as a wind speed at 10 meter high in open country. Okay, and is multiplied by the logarithm of z. Z here is the height above the ground, and Z0 is the roughness length of your site. So here we express a change of wind speed, of mean wind speed, from reference wind speed at 10 meter high in open country to another one at Z0 with, and you can express also take into consideration the gradients of flow with altitudes. So we can transfer, for example, from this is 10 meter reference to 50 meter to 100 meter to 25 meters. You just have to apply this law. So this work when you want to change from open country 10 meter high to another land occupation and when it's flat. Okay, let's move to the next subject. So now the idea is how can I assess my roughness on my site? Because I said I explain theoretical law with uniform roughness, but the reality is not that simple. If you want to transfer wind data from the airport, so it is on the top left corner, to your site represented by the house, you have a lot of land occupation. So you have a forest, you have open country, you have a city. So you need to take into consideration this kind of patchwork. And the second thing is how can I transfer, get an idea of value of my land occupation. I've provided some classes, but you could have more classes. So I'll give you here two examples of land occupation map. You have a worldwide land occupation called ESA, CCILC for land occupation, with 22 classes, but only one for urban class and a spatial resolution of 300 meters, which is quite interesting. You could have a look if you Google Global Wind Atlas. So it's a wind atlas over the world. He also provides the roughness length over the road using this ESA land occupation. So this could be a start point. We have in Europe a program called Corinne Land Cover since I don't know, since a long time, that cover with 44 classes and 4 classes of urban area with a resolution smaller than 100 meter. So it's very interesting. I know there are many more programs around the world, but this is the most useful for in our countries. Okay, so now I've got my land occupation map. I can convert to numbers. Next question. So how can I mix that information? This is the next slide. I would like to refer again with a Eurocode. So again, here we are dealing with safety issue. We want to make sure we take into consideration the windiest condition sector. So the idea is going to we will have a look on we're going to base on analysis on our buildings with a certain height. This is the rule on the right side. We have the height of our buildings, let's say 30 meter high. What will be the influence around my building? How far I need to take into consideration my land occupation? So we have the answer with the Eurocode. If I have a building of 30 meter high, I can apply the rule here of radius equal to 23 multiplied by h power 1.2. with a minimum of radius of 300 meters. So this will give me, with a height of 30 meters high, it gives me a radius of infer of 1.3 kilometers around my building. So have a look with this radius with a sector of 30 degrees. This is on the right, sorry, on the left part, you have a sector rule every 30 degrees, and you have to look what will be the lowest roughness length that represent 10% of the surface. So that's why it will affect much more the wind than it is actually. It will reinforce. We are talking about safety. In the reality, we should have a mixed, not really an average, but something in between these two rules. It is a bit more complicated than that. So what we can propose usually it's tools, advanced tool, to have a good order of this average of land occupation. So we have our in-house tool called WT, or you can use wind tunnel for experiments, but you need more advanced tool to take into consideration a mixture of all that land occupation. The tricky part. Okay, so I think now you understand that it makes a lot of difference to be sure that you need to take into consideration all of that effects. So let's move to the next slide. I would like to give you some what I called first aid kit, in addition to what I said earlier. But this is very, very powerful and I think simple. What I'm going to say. So next slide. I would like to present to you. Yes. The first thing is which weather station I should pick. If you have the choice, of course. You should always pick the weather data at the airport. Why? Two reasons is the quality. Because at the airport they make sure that they have relevant and good data for the airplane safety. And they are recorded 24 hours all the year with high frequency. So you are make sure that this is really well set up. Whereas in the downtown, you have no idea the quality of the data. The other reason is that it is very less disturbed by the environment. At the airport, it is usually in open countries, so there is no obstacles nearby the mast data. Whereas in the downtown, you have buildings around that's going also evolve in the time. That's if you are looking over 10 years, the the buildings will maybe change, so the wind data will be affected by all those buildings and the change of buildings. So that's why you should always pick weather station at the airports. Okay, this is the first thing. Second thing on the next slide is always check the weather data. So there are 5 rules to follow. The first one, if you have a look on the raw data recorded, and it is on the second top graph, which is highly turbulent, you see with the black line, it is really disturbed. So these are the raw data, let's say every 0.5 seconds. It is too raw for our purpose. So if we average, there are different kind of average. There is an average every 3 seconds. This is the blue line. And what we're going to use is mostly 10 minutes average for our purpose for wind comfort. 10 minutes average it's the most useful for wind comfort. I know that in other country, Netherlands, sorry, they use hourly data average, but the standard is mostly 10 minutes. You can have other rules, but this is the standard 10 minutes. The next question is what will be the frequency? So you have different frequency. It can range from 0.5 seconds or 1 record per day. But what we usually use is hourly data. So every 1 hour we have a data which have been averaged over the 10 last minutes. This is what the common practice in wind engineering. So you have to make sure that this is the case. Third thing is the units. This makes obvious, but you have to make sure. If it use SI standard, it should be meter per second, but you have to make sure. Third thing is the quality checking. Always check that the mean for the basic, check the mean and the max for the mean and the direction. I'm thinking about when you have a value of 999 for direction of wind speed. So this could be a case when you have a problem with a sensor, when you have a failure with a sensor. So if it lasts for a long time, you have to be aware it could be a failure of the sensor, so you should get rid of that on your data. So always have a look on the mean and the max of those columns. The last thing and very important is the time of record. To be relevant in the meteorologic world, you should have at least the last 5 years, and I recommend that 10 last year, to have big events of weather data. I'm thinking about El Nino, La Nina. This can affect your data, and this is very large scale that should be incorporated in your data. So 5 years is the minimum, 10 years is better. And you should always take the last 5 years or last 10 years. If you are getting very old data, wind data, it could not reflect the reality of the surrounding of your project, because the city expand a lot and it can affect a lot your wind data. If you are completing data with 20 or 30 years back, the city has completely changed. So it has completely evolved and it may affect your wind data. Okay, so these are the basic rule. Okay, so next slide. Another important rule is that your obstacles can affect your wind data. So be sure that else you don't have the obstacle around your wind data, or else you take into consideration these obstacles. Second thing is that always advise to transfer from the airports when it's possible to a point above the city and not inside the city. Why? Is because, as I said, the obstacles will affect your wind data, a single obstacles. So it is not the best way to do it. You should always have a statistical approach It's better to transfer above the influence of a single building, so above the city, and to consider the change by logarithm law with the change of land occupation, and not by the influence of a building by the wake effect or Venturi effect. It's better to have a statistical approach, overall approach. So always above the city. Okay, let's move to the next slide. So I would like to focus now on some example and the difference I will have between simple law, as I explained before with logarithm law, and the one which is more complex, such as CFD, and to see if there are big holes and how it is important in my wind comfort analysis. So I will focus on 3 examples. Let's start with Marseille. I will use wind law approach. So remember that we are starting from the airport always. So let's start with Marseille. On the next slide. Okay, thanks. So you have the case where you have airports. You can have a look on the left bottom image with the arrow from the airport to the city. You have land occupation on the bottom image, and you have orography on the top image. So we are transferring from the airport to the city of Marseille, which is in the suburban area. So suburban area are picked in the right line, the right coefficient, and the right roughness length. This will give me a ratio between my wind speed at the reference and the ratio at the wind speed at 100 meter. This will give me 24% more wind speed at 100 meter high above the city than at 10 meter high above the airport. So that's what give me the logarithm law. And now let's compare to what give me the CFD approach. CFD approach with our in-house tool on the next slide with WT that take into consideration large-scale effects or the roughness effect or the orographic effect over 10 kilometer radius. So from the airport to the site, what we could see that in this case, my logarithm approach provide me same value than my CFD approach, 24%, sorry. Roughness, 24% more wind speed than the airport, and the CFD give me 25%. So this is good numbers. So I could, in this case, could get rid of CFD. And you see that the wind direction at the airport and over my site are roughly the same. The topography didn't affect, so that's good. Let's move to the next example. This is Paris. So again, I transfer from the airport to the city. So here, airport is a military airport in the southwest Villa Coublé to the city. So I apply again log law in the suburb, and this will give me same number, 24% more wind speed. Notice that here we have a change of roughness, which is not really as uniform as Marseille. On the bottom left image, you have different green color That's because you have open country, you have forest, you have city. So it's not really uniform roughness compared to Marseille. So what we'll see the CFD, so more complex approach for the wind transfer. On the next slide, the CFD approach will give me actually more wind speed, much more, so 45% more wind speed, because my land occupation is not as uniform as I claim in the log law. It is actually smaller. So when you have smaller wind speed, you're going to accelerate. So the log law using uniform roughness length at my side does not work in this case. You should take something maybe smaller in your roughness length, which is not easy to interpret. So here you see you have 20% error between these two approaches on the mean speed. So you could say 20% difference. Is it important or is not important for my purpose, for to get the good classes for wind comfort? So let's see on my example in Paris. So I represent with my criteria, French criteria of 3.6 meter per second, threshold with 1 sigma for turbulence. And I compare with the log law approach with the CFD, and I compare with color. So for different comfortable activities, when it's purple, it is comfortable for any kind of activities on the right side of the color panel. And if you move to the left side of the color panel for red color, it is not comfortable. So you see there are big difference between these two images for the red. You are more red color with the CFD because you are more wind speed. Remember, it was 45% more wind speed versus, I don't remember. Sorry, I don't remember the figure. But you are more wind speed, 27% more wind speed between these two approaches. So that's why you have different color and makes a lot of difference in your data and your post process. Another example for overseas in Nouméa, overseas French territory, New Caledonia. So here we want to transfer from wind data inside the city to construction site. Here we cannot apply our log law because our reference wind speed is not at the airport. But you can trick it. You can derive UREF at your mast data, derive UF, and to get what it should be at open country, and you re-inject inside your equation, and you will get proportionally the new reference wind speed. So it's possible to derive it, but it's not directly from the formula. Even saying that, you could do that, but even saying that, in this case, it will not going to provide you a good results because on the next slide, what is here going to affect a lot is the topographic effect, and the CFD show that from the airport to your site, you have actually a very strong orographic effect. You see the wind rows is not the same because you have, well, in this case, it was very important. You have some volcano nearby, so it is a bit over exaggerated. But the idea that the wind direction can be very different from the airport. So this is where you need to get more advanced tool than a simple log law, because you cannot forecast the new direction. When it's flat, nothing happens. But when you have strong hilly place, and it's where troubles appear, I would say. Okay, I think I have one next slide to introduce to you, is where can you collect data. You are probably familiar with this, but for those who are not, on the next slide, I've gathered some sources. So there are, you can ask to the national weather data provider. We have Meteo France in France, you have Met Office in UK and other countries. You can ask to free the weather data provider. I'm thinking about NOAA in US department. So it's a worldwide organization for the weather, and it collects all national providers from all national provider data. So it's very, very nice. The only drawback is that it is raw data, so there is no to say checking of the data. You could face some strange issues, such as technical issue with the probe, so be careful of that. Another one is EPW, and EPW is more clean, so it reflects more the reality, but is not as spread as the one from NOAA. You have software. I'm thinking about Meteonorm. He collects data from all the world and make his own recipe to clean it. Another one is mesoscale data, which is worldwide data. Here you have some provider. We can do also this kind of analysis every widely for the last 10 years. And in Urbawind, we have also database for wind data over Europe. We have North America and Israel nowadays. So I think I cover my webinar. Thanks for listening, and I'm sure that you have many questions. So let's move to the question session. We have some times. Let me scroll with Guillaume.
Yeah, thank you, Guillaume. And of course, if we don't have any more time to answer all your questions, feel free to reach us through our emails. And also, you will have an access to this replay, the replay of this webinar, and a global answer to all your questions. We didn't have the time to answer it yet at this moment. And I think we have some questions for the moment. Maybe you got one, Guillaume?
Yeah, anyway, I'm reading it. I have a question. Does Urban compute the wind factor in the city in case of using weather data from the airport? So it is what has explained you. The weather data at the airport are raw data that has been recorded in this kind of land occupation, so usually open country. So you need to change it to the environment you got in the city by rules I provide you with program rules or your own recipe, and you need to affect the new roughness length to affect to change the gradient of velocity due to the change of roughness. Is Urbawin database, does it take into consideration the change of roughness and topography? Yes, we did uh, CFD approach using our in-house product WT to correct the roughness effect and the orographic effect. So you don't have to modify it. And the other question, do we need to correct the EPW? It depends also of where come from the EPW. Is it at the city or is it at the airport? If it's at the airport, you need to change it in the right column, the mean speed. You need to correct by the new roughness length. If it's in city, it should be okay. Just be careful. You should always, you should pick data above the influence of obstacles above the city at 100 meter high or 2 meter high. So you need to change by the gradient law, the wind speed. Okay, there are questions asking about effects of the orography between Marignan and Marseille are not that important for the orography. It it doesn't seem to be. It's probably because we are far away from the hill effect. Maybe the rule or 10 times the height. So it should not influence. We are not in the wake effect of the uh, yeah, of those obstacles. Okay, so we have another question about the data itself. So you got hourly data, and normally they are average over the 10 last minutes. This is the standard procedure for wind data. The international standard. You just have to make sure. I know in NOAA, in the README file, he explain you the details of the averaging. So it's clearly say that they average 10 last minutes. But you can ask to your provider which kind of average he use. Sorry, I'm not sure to know this kind of profile, ASCE profile like BCD, or it's probably Australian and New Zealand. Probably I don't know this, but it looks like very much what we have in Europe. We have different profile. We have 4 kind of land occupation. Sea, open country, medium, and high city. So it looks like what you got in Australia and New Zealand. And we are using that in Eurocode for wind safety issue. But it is very interesting to know that it exists also in Australia and New Zealand. Someone asked me to summarize when do we need to use airport data or when do we need to use a local meteorological station? Okay. So I prefer data at the airport, but it should not be too far away from your project because you will have what we call mesoscale effects. So it shouldn't be more than, let's say, 30 kilometers away from your project. And it should be the same land occupation around your buildings, between the airport and your site. If you have hilly condition, you need to take into consideration that uh, whether a local meteorological station is good, but it shouldn't be too close to a building. Otherwise, it will be disturbed. The data will be disturbed by the buildings, and so you need to correct it. And this is a tricky part. How can I correct it when the city evolve? How can you correct it? So this is very, very tricky. So I prefer to get weather data which is not disturbed by the environment at the airport and to correct it statistically with log law or exponential law or power law, whatever you want.
I think we will stop here for the question
Yeah,
because we are running of time at this moment. But feel free to reach us with your question by email, and also you will have a summarizing document with all the answer to your question at this moment, and you'll send us through the panel chat. Uh, Finally, we thank you for your time and your participation to this webinar. And also, you will have an access to the replay of this webinar. So feel free to watch it again if you have more questions, more details you know about simulation, and feel free to reach us also if you have some studies around your meteo accommodation. So thank you for your time
it
and
was
see you
very nice
next time.
to be here because I can see that from the question you enjoy this webinar, and it's a good news that we can go further if you have more questions about that subject. So very happy to be here today with Guillaume and with you. So have a good day.
Have a good day
Bye.
and thank you. Bye.